Hi, we are back for the oral session 4. Our first speaker today will be Kelly Cristina. She works at Federal University of Rio de Janeiro, and she will talk about a generalized exponential growth model under adaptive cluster sampling.
Okay, thank you, Thais. Thanks for coming. Thanks for the committee for the opportunity to explain my work in this session. So this is a joint work with Fernando Moura, who is professor also at UFRJ. And the main aim of this work is to propose a superpopulation model for rare and cluster populations, which will present some behavior of increase or decrease over time. And we will suppose that the samples of this population is selected by adaptive cluster sampling, which is an informative planning, so it will have to be considered on the inference. Okay? So the motivation of this work, as I said before, are the rare and cluster populations, for example, people with rare disease or drug users, recent immigrants in origin. Population like that tends to be distributed in a small number and clustered in some regions. Okay, and one problem with this population is the selection of the sample, because traditional grid cell planning will generate poor estimates because there is a large number of zeros in this population. So here I have for you a beautiful illustration of population like that. This is the blue-winged teal in Florida in 1992. That data set is also described in this paper, okay? So they superimposed a regular grid in this region and count the number of blue-winged teal in each unit. So the empty units mean that there is no blue-winged teal, okay? And the numbers are the count of the blue-winged teal in these units. So you can see that this is a sparse population clustered in some regions. So populations like that are our motivation for this work. As I said before, traditional grid cell planning can generate poor estimates. So Thompson, in 1990, proposed an efficient method to select samples of populations with this behavior. This is called adaptive cluster sampling. And here I have an illustration for you. So let's suppose that the points are the observations of interest, okay? So the sample starts selecting a simple random sampling of units, and we will observe these units. And if this unit observed contains the observation of interest, we will survey also the neighborhood of this unit. So, for example, this one and this one contains the observation of interest, so we will follow like that, okay? And if this unit also contains, we will also serve its neighborhood, and we obtain something like that, okay? So the final sample will be these two groups and the units in grade that was selected on the beginning by the simple random sampling, okay? So we can see that the selection of the sample depends on the values of the variable of interest. And the other important observations that the final sample size is not known. It's a random variable, okay? So let's introduce some definitions that will be very important in this presentation. First, I will call by cluster all the group. Network are the units in this cluster that contains the observations of interest that are represented here in gray. And the remaining units are the border units. So mainly the concept of network will be very important for us. When we're dealing with finite population sampling, we can use two different approaches. The first one is the design-based approach. Okay, so in this case, the population is treated as fixed, and the mechanism of selection of the sample is represented by a probability function defined on the set of all possible samples. So the randomness is the selection of the sample. The second one, the model-based approach, we, in general, use superpopulation models. So we define the model for all the population. And the values of the variables of interest are treated as realizations of random variables. And particularly in this work, we are interested in the second one approach, that is a superpopulation model. Okay, and as expected, we will use a Bayesian paradigm, okay, to do the inference for the parameters. But have to pay attention here, because as I said before, in adaptive cluster sampling, for example, the sample selection depends on the values of the variable of interest. So the sample will bring information for us to estimate the parameters. When we have this behavior, we can write a joint likelihood that will depend on the variable of interest and on the probability of inclusion vector, the inclusion probability vector, sorry. This is well described in this book, okay? And so, as I said before, we will have a complete likelihood that depends on the variables of interest and the probability inclusion vector, and that can be partitioned in this way. And this is defined for all the population. So after we observe the sample, we will have an observed likelihood. So this is, we will have a likelihood that will depend here on the values observed on the sample. Okay. So this will be used we will use this in this work because adaptive cluster sampling is non-ignorable, okay? So the model that we will propose needs to incorporate the adaptive cluster sampling in the likelihood. On the literature, we have a superpopulation model for this case. This was introduced by Ripley and Welsh in 2008 in the Bayesian Analysis Journal. Here are the main features of this model. First, the model likelihood is constructed in the level of the networks, not in the level of the units, but in the level of the networks, what will facilitate, in some cases, the inference. And also, the model will suppose homogeneity between units that belong to different networks, okay? What can be reasonable in some cases, but strong in other cases. But we will use this model, we will extend this model for cases when the rare and cluster population presents some temporal dynamic of increasing or decreasing over time. This book, 2004, presents some studies, some real studies, that show that this temporal dynamic is expected in population like that. Particularly, our proposal will be formulated by using exponential growth models, okay? And we will suppose that the sample will be selected by adaptive cluster sampling. Here, there is an illustration of the dynamic of interest in this work. So we can see that as time goes by, the networks are increasing, and eventually, some networks may appear in the population. We are particularly interested in this behavior or in the reverse. So this is the temporal dynamic that we are interested in. Before I will present the model for you, I think it's easier to understand the model variables looking at this illustration. So I will call as n the size of the regular grid. Xt is the number of non-empty units in time t that are represented here by the color blue. Rt is the number of non-empty networks in time t that are represented here in red. Ct is the size of each network, and Yt is the count inside each network. Okay, so it's the total inside each network. And here is the proposed model. So what is in red is our extension. So first, some observations. All the distributions are left truncated to guarantee that there is at least one non-empty network in the population. Other important observations are the parameters alpha and beta. They are responsible on the control of the sparsity and clustering of the population. So we decided to introduce the exponential growth model in this parameter alpha. So it will vary on time. Other important observations that Y, as I said before, is the count inside each network. So yi is the count inside network I at time t. It follows a truncated Poisson. This parameter is not exactly the mean because it's a truncated Poisson, not exactly the, it's not the Poisson distribution, but this mean is approximate to this. And here you can see the hypothesis of homogeneity between units which belong to different networks. And we can see also that they suppose that the count inside each network is proportional to its size. So we introduce the time in this case using this exponential growth model in this parameter. And here's as I said before, we will introduce the probability of selection of the sample, because in this case it's reasonable because we are supposing that for each time we are selecting adaptive cluster sampling. So here's the probability of selection of the sample at time t. And what we have behind this expression is that the probability of selection of one network is proportional to its size. As I said before, it's a superpopulation model. So all the variables are defined for each unit in the population. So after we observe the sample, we'll have some information about each variable. So after we observe the sample, we can partition all these variables in this way. So you have an observed component and an unobserved component. And the goal is to do inference about the population total for each time. This exponential growth model before, as I said, alpha and beta will control the sparsity and the clustering of the population. So we can use this idea to construct our prior distribution. So we will use here informative prior distributions. And the parameters A, B, and C of the exponential growth model are responsible for about the behavior of the curve. So, for example, if C, in this case, we are only interested in non-explosive process. So, in this case, C is negative. And in this case, in this one, where we have an increasing behavior, we have that B times C needs to be positive, and the other B times C is negative. So we will use this to construct our prior distribution. And here are the prior distributions, independent prior distributions assumed for each parameter. So C, we will assume a truncated normal on the negative. A and B, we suppose a joint distribution, mixture of bivariate normals, and which the first component represents the increase, and the other component will represent the decrease. Well, this work is still in development. We did some simulation studies, and here I present one for you. In the simulation studies, we sampled several simulations, so we generate several simulated cluster populations, and from these populations, we select adaptive cluster sampling. And fixing these parameters and these values, and so it's a simulation study, and we studied some frequencies or properties of the Bayes estimators. So we compare our proposal with the other two approaches on the literature. So the first one is our proposal. The second is the model of Rapley and Welch fitted for its time independently. And the third one is the design-based estimator proposed by the initial paper of Thompson in 1990, implemented for each time independently. So we compare these three approaches. Here we have the coverage of the 95% HPG intervals for the base estimators for the population total, which is our main interest in this work. So you can see, first you have the independent fit of the Rapley and Welch's model and our proposal. We can see that both underestimate the desired level of 95%, and the independent fit has a better result than ours. But on the other hand, we can see the width of the HPG intervals, and we can see that the dependent one has more inaccurate intervals. The third one is the square root of the relative mean square errors of our proposed and the dependent fit, and we can see that our proposal presents the independent fits present larger errors, and the last is the square root of the relative mean square error for the three approaches, and you can see also some advantages on using our proposal. But as I said before, it's a work in development, and there are some results to be improved. So here are the main conclusions. We consider the problem of estimating the total population, a rare, clustered, and now dynamic population. We modeled the observed counts grid cells along periods of time, and we suppose that the samples were selected by adaptive cluster planning. We did some simulation studies. We evaluate the model's performance in this case, and we see some advantages in using our approach. And finally, on the beginning of this talk, I said for you that it's an extension of the Rapley and Welch's model. And one hypothesis here is that there is homogeneity between units which belongs to different networks. So it can be questioned sometimes. There is still a work developed by me and Fernando Moura. It was accepted on Bayesian Analysis, the journal. If you are interested, you can see this in the website of Bayesian Analysis as an advanced issue. And there we consider for the static case this problem of the heterogeneity between units which belongs to different networks. So as a future work, you can extend also this model to dynamic cases. So here are the main reference. This one is that I said for you. Okay. So thank you so much. Obrigada.
Any questions? No? Obrigada, Kelly. Vamos esperar pouquinho. We will wait a bit to go to the next talk. It's Anna, right?